This is the walkthrough of template.cpp on your Canvas page. So this is an example program that shows you how to use a template with both a function and also a class. Just kind of in broad strokes, use a template when you need to have the code be exactly the same, but you want to be able to handle different types. So you want an int handled the same way as a float, handled the same way as a double. You can use overloading when you want to have the code be slightly different with each different type. So C++ does it both ways. Overloading's where you just define the function with the different types over and over and over again. And then templating's where you have this one set of code and then you add the template statement above it, and then you use your type names to specify the template. So let's take a look at the function. So here's our function. It's new underscore ABS. It accepts a variable that's passed to it, and it returns a variable. So we have this statement template, and then the less than type name, and then whatever you're calling the type name, that can be any valid identifier. Your book tended to use just single capital letters, so I'm just using that same format. And then the greater than to close out the set of template. Then anywhere you would have this particular type, so for example if this was int, then new absolute value would receive an int called input var, and it would return an int. So anywhere we'd have int, we would just replace it with t. If we had float, then it would receive a float, return a float. So we've replaced both of those with t. In addition, your function may have other variables that are set up that'll also need to have that type, and so then you can see how we're using this type t to also specify the output variable, because the output variable is being used as temporary storage before it's returned. This is just an example. There's no reason really to set up this output variable other than the example, because you could do the whole calculation just right in the return statement if you wanted to. So this one's just an absolute value, so it's just taking the input, multiplying it by the input, and then taking the square root, just the classical definition of absolute value. Let's take a look at how this runs. So let me go ahead and run it. And let's look down in main and see how this is set up. So in main, we've defined an integer of -10, defined a float of -12.3, and a double C of -1.234 and some change. So then when we run this, we just call the function. So this is a cout statement. We've got the function just right in the cout statement. So it's new underscore ABS. And when you send it an int, it goes back up to the function, and it says, okay, input var was an int, so the programmer must have meant for t to be int. So this becomes an int here, an int here, an int here, and anywhere you had that same type name t. Let's scroll back down to main. When you call it with a float, it's the same thing. It just converts everywhere there was a t over to float, and then if you called it with a double, it would convert everywhere there was t over to a double. If you called it with a string or something like that, then you might get an error depending on how these operators were defined. So if string didn't have an operator and a square root, then it would cause you an error. But any particular type that you send it, where you've got a asterisk, a multiplication operator defined, and you've got some way for it to take the square root function with that type, then it'll be able to figure it out and complete the calculation. So you can see why we would want this as a template, because it's the same code for an integer, it's the same code for a float, it's the same code for a double. And then you can see that it works here. When we've got -10, we get 10, -12.3, we get 12.3, -1.1, we get positive 1.1. So the absolute value worked there. Now, when you're doing a class, of course, it's a little bit more complicated, but there are some similarities. So here's our class, and this is our class prototype. So the class is called example. And then just right above your class prototype, you have the same template statement and the same format. In this case, we want to define multiple type names. You don't have to do that, but this is just an example of one where the class had multiple type names. So you use the word type name as a keyword, and then name each of your type names with any valid identifier. Again, just keeping with your book, I'm just using capital letters. And then within your class prototype, anywhere you want it to be this particular type name, you just use U. So this would be standard vector int, right? Well, instead of int, we're going to just use U. So then U will be set when we call the instance of the class, and then it'll be set if we call it with an integer here, then everywhere we see U, it'll become integer. If we call it with a float where we have V, then everywhere we have V will become a float. You can see we've got this set up to where it's working with vector. We've got this where we're defining some variables. We've got some constructors, the constructors taking the two types as well, and then we've got some functions that are returning, and they're returning type U and returning type V. Now let's look at how we've got this enabled with this class. So here's our enabling code. This is our default constructor. So it's that same statement. You could just literally come up here and grab it and copy and paste it. But then there's one thing that's a little bit different with this constructor. Normally we would do example : example open close parentheses, but because we have the template, we need to include that, so it'll be example less than U comma V greater than : example. So there's our constructor. Here's our parameterized constructor. Same format, but now it's receiving a variable of type U and a variable of type V. This class is not really doing anything useful. It's just an example of what the code would look like. And then here's some of our member functions. So again, the same template statement. This is return type U, and then there's our class name again with the U comma V in there. And then you'll notice when we run it with the class, let me pull the output up here, that it's going to look really similar to how we ran vectors. So remember, with vectors it would be std : vector, and then there'd be a less than, and you'd put your int or your float or your double and then your greater than sign. Vector is actually using a template. We've just never really talked about that that's what it's doing, but that's why vector works with all these different types. And so when you call this programmer defined class, it's really the same way. It's your class name, and then just like you did with vector, this one now takes two type names the way that we have it set up. You just put the two type names in there. If you're doing your default constructor, then it's just the name of the instance. If you're using your parameterized constructor, then it would be the two variables or the two numbers. In this case, just these two literal numbers that we're sending up there. Make for sure if you're using literals that they match. So the 1.5 does match the float, and the 2 does match the int. And then you can see here when we call these functions, we don't have to do anything special. We've set everything up when we created the instance of it. Then we just call the functions the usual way, and they return the variables that are in there. So this idea of templating can really save you a lot of time if you're coding some kind of generic code that can run with all these different types. But again, if you need to have your functionality be slightly different, you need that code to change slightly for each different type, that would be the case for using overloading instead of templates. Templates are where you want exactly the same code regardless of type. Thanks for watching.